If you're new to this channel, you may consider subscribing and hit the bell icon so that you continue to receive the updates. Please share it with all others who might benefit. Let's get started. All right, so far we discussed market basket analysis and we took a straightforward example where we talked about two items being ordered from a restaurant and how we could calculate their support and confidence. But the challenge comes when we try to scale it, because the restaurant might not be selling just these two items. They may have more items. Let's look at an extension of this and try to understand the importance of the Apriori algorithm, which helps us solve this problem. So let's say the menu contains 100 items, but for time being, we're going to concentrate only on 4 items. And these 4 items are, let's say, a club sandwich, a classic coffee, a cheeseburger, and an orange juice. These are the 4 items out of total 100 items that the restaurant offers in its menu. Now let's try to understand in how many ways can an order be placed where from none to all 4 items can be ordered. So there's a possibility that the restaurant has other items and the customer placing the order doesn't choose any of these 4 items, chooses from the remaining 96 items. And there is a possibility that somebody likes all these items and orders them all together. All these 4 items are on the same order. Let's try to understand it a little closely. So we'll have to build cases. First is that none of these 4 items have been ordered. Second is maybe only one of these items is being ordered. So either it's sandwich or coffee or burger or juice. We've just simplified the notation. We've just taken the first alphabet. Another possibility is that people choose 2 of these 4 items. So it could be a combination between a sandwich and a coffee, a sandwich and a burger, a sandwich and a juice, a coffee and a burger, a coffee and a juice, and burger and juice. There are more possibilities. We could be looking at a combination of 3 of these, and you can understand what these represent. And the final possibility is that somebody orders all 4 items. Now, does this look familiar? How would you know this if you have, let's say, a long list of items? We only considered about 4 items, and that's why we could build these cases. But if we have, let's say, M items, how would we work this out? Well, actually, this is a concept of binomial distribution. You all must be remembering when we have to make a choice out of certain given options, this is how we go about it. So when we say none out of the 4, it will be seen as 4C0. When we say just 1 out of the 4, it will be 4C1 or 4 choose 1. Likewise, 4 choose 2, 4 choose 3, and 4 choose 4. And if you add all these up, you might have studied something similar in binomial distribution. If you add all these up, the total will be 2 raised to the power m, where m in our case right now is 4. So 2 raised to the power 4 is nothing but 16. These would be 16 possibilities that you'd be looking at right now. So in general, if you have m items taken together, the total possibilities would be 2 raised to the power m. And this, of course, gets a little more complex. So to understand the challenge better, let's say we are looking at certain orders and some items being ordered. And you'll have more transactions. We've just taken a quick snapshot of maybe 6, 7 orders. That's what we're looking at. So let's say we have a total of n orders that the restaurant has catered to. And the average order length is L, which is nothing but the average number of items that are being ordered. Now, we cannot do much about the orders being placed because these are placed by the customers. If you're listed, you're there to do business, you'd want more orders. That's fine. Average order length, if that helps you get more revenue, why would you not want to have a higher average order length? All you're trying to do is, can we simplify the calculations? But as far as the candidate items are concerned, or the possibilities in which these items could be paired are concerned, that is a complexity that we want to solve so that we can come up with the right combinations. Maybe we can promote them as the combos on our menu, which are already popular. So we don't want to be optimizing n, we don't want to be optimizing L, we want to be doing something about this 2 raised to the power m. Why? Because this is what makes the computations pretty complex. If you know about the complexity of algorithms, the order of this complexity is going to be n multiplied by L multiplied by 2 raised to the power m. Now, to optimize for this 2 raised to the power m, we take help of the Apriori algorithm. Let's look at the same scenario, and let's say you found out that juice itself is not a frequent item. So we are looking at juice as a separate case. Now, in the subsequent layers, if you look at it carefully, anything which is a combination with juice will also not be a frequent item. So in a way, when we look at paired items, the combination of a sandwich and juice, a coffee and juice, and burger and juice itself would also not be a frequent combination. Because to begin with, juice itself is not a frequent item. And if we roll this up further, even when you're looking at 3 items being ordered, you would find that the combinations associated with juice will not make sense. And so would be the case when you're looking at all 4 items being ordered. So if you see, from a complexity of 2 raised to the power m, now your scope is limited to just the combinations which are indicated in these blue color nodes. And let's say we are trying to work closely on a combination which puts 3 items together, then we don't have to get confused about 4 possibilities here. We can zero down to just this one possibility which talks about the combination of sandwich, coffee, and burger. So in a way, the Apriori algorithm is helping us reduce the complexity because our scope is now being reduced to limited few cases. Now let's closely understand what is this a priori property. The a priori property states that if an item set is frequent, then all of its subsets must also be frequent. So to put it the other way, if the subsets are infrequent to begin with, then the supersets will also be infrequent. Let's take an example. If juice itself is not a frequent item, a combination of juice with sandwich or burger or coffee isn't going to be frequent either. That's what we discussed. So how do we apply this to our market basket analysis? We set a minimum support threshold to reduce the complexity. That will be like a hyperparameter that is controlled by the person conducting the experiment. But there's one more level of filtering that we need. Let's go back to the problem. Let's say we zeroed down to this combination of sandwich, coffee, and burger. Now, there are multiple rules that can be generated. And end of the day, through a market basket analysis, you're interested in generating the rules. Let's look at the possible rules. So generally, the item set which is recommending is called antecedent, and the item being recommended is called a consequent. So we could say that a combination of sandwich and coffee recommends a burger. We could say a combination of sandwich and burger recommends a coffee, or we could say a combination of burger and coffee recommends a sandwich. So how do we zero down to a better rule? Once again, the a priori property will be used, but this time on the confidence. The rule having better confidence is the one that will be considered as more meaningful. And what is this confidence? We discussed it in the first video. The confidence is nothing but a conditional probability. So a conditional probability of burger given sandwich and coffee, coffee given sandwich and burger, sandwich given coffee and burger. Whichever has the higher probability, that makes more sense as a rule. So we've just taken some limited examples of rules here, but you can imagine it could also be the other way. There could be one item recommending 2 other items with it. That's also possible. But we've just taken a specific case. Once again, to filter out the most meaningful rules here, you will apply the a priori property. So just like we could set a threshold for support to simplify our calculations at stage 1, we could also set a threshold for confidence to reduce the complexity further. So to put it together, in a market basket analysis, while the basic concept of probability is pretty much intact, it could lead to computational complexities owing to multiple possible combinations. In order to solve for it, the algorithm that comes pretty handy is known as the a priori algorithm. Now, a priori algorithm or a priori property is not just associated with market basket analysis. It's something to do with a basic logic that if we talk about a superset being frequent, then its subsets must have been frequent. We kind of used it the other way. We said if a subset is frequent, only then a superset would be frequent. Or if a subset to begin with is infrequent, then a superset is not going to be meaningful. And that helps us resolve the complexity problem at 2 stages. First, by setting the right threshold for support, and second, by setting a threshold for conditional probability when you're comparing between the rules. Hope this comes handy, and you'll see more of this as we move to the hands-on piece. How do we actually apply these thresholds? Because these are hyperparameters. You wouldn't know the right value, but you'd want to experiment with a few values and come with the right suggested input. Thank you.